All right, welcome back. This will be the next talk on track 1. Here with me on stage is Kirils. He will be talking about reverse engineering intercom systems. I'm looking forward to this talk. Sounds really interesting. Please give a warm round of applause.
Good morning, everybody. It is a real pleasure to be back. Second year in a row. Very unexpected for me. But here I am, just after the keynote. So those of you who have not yet met me, that's me when I work. I run my own company, which is rather boring. I didn't ask for it; it just happened over the years. So when I have some free time, I love to hack because running the company involves a lot of non-hacking stuff. So some of the things I research are reverse engineering projects, such as this one, and that's what I'm going to talk about here today. Some of my other presentations include more ephemeral topics like privacy and digital rights and stuff like that. What I'd like you to take a look at later on is kirils.org. It's a website that has most of my slides, more than 100 presentations. It has videos as well. So different topics from assembly and reverse engineering up to how the IT is going to look like in the future, the whole shebang. And this presentation here is aimed at people who are starting with reverse engineering. Of course, there's some hacks as well, some ponages will be presented, but I structured it in such a way that if you feel like you're new in reverse engineering and you'd like to start out, I hope this is going to give you the required information that you need to begin your journey. So that's kind of what I'd like to achieve here. So the presentation here is about intercom systems. So that's an intercom, right? The thing you have in the bottom of the building. It may be a commercial building. It may be a multi-tenant house with multiple apartments. So a visitor can call in, or if you have a RFID card, you can badge in and you can talk to specific apartment or specific office who can then let you in or not let you in. And there's sometimes a camera as well that allows you to take a look at it, right? So that's the outline, right? I'm going to talk a bit about the motivation, and as I mentioned, I'm going to be talking a lot about the process. And for about the first third of the presentation, I'm going to be talking about the mistakes I made. So, basically, I hope that what I thought when starting this, I thought, it would be interesting if I would just, take whatever is in my home, whatever just is laying around, and can I use that to get to the bottom of this system and see how it's working. So right, basically what happened is I got an apartment, and for the first time ever, I got an apartment that had an intercom in it. It was a new thing for me, and I looked at it at the terminal, and it had this sticker on it that basically says, if you want to, you can just take your. It's called a phone unit. Yeah? Take your phone unit that you have in your apartment inside it, take it away, and put a different one, and it will just work. You can upgrade it. In this case, I do have the one on your left there that has just the phone, but I could theoretically upgrade it to one with a video screen, and then I could see what's happening because there is a camera down there. Also, I work remotely. We've been doing remote work in my company for the whole duration of it for more than 13 years. And I can't always walk to the door. I have a bunch of meetings, and people bring deliveries, and then, it's not far, but it takes a while. So I had an idea that I would love to have a button on my computer that can open the door remotely and maybe even talk to people remotely, right? Have robotic voice talk to them. So I started looking into it. This device is created by a Spanish company called Firma. They are very, very worldwide. They have offices in Australia. They have offices in Singapore. And they're from Spain themselves. And they've been around for about 50 years. Those guys, and I really would love to give a shout out to them. They are really, really innovation-oriented. They have a bunch of patents coming out every couple of years. They keep inventing new stuff, which is really cool. So I read about the device, and basically what it says is that it can use any kind of cabling. Any cabling you have in your home, it's going to work, which I thought, wow, that's interesting. Then I read a bit more. It said basically you need just 2 wires. It's a bus infrastructure. Bus infrastructure means there's like a connection. We can call it horizontal or vertical, doesn't matter. Let's say a horizontal connection, and different devices connect to it. And all the devices, at least on the hardware level, see the same data that's on the bus, similar to the bus you have on your motherboard, for example, or many different kind of digital buses. So that would mean that technically all the devices in the building receive the same data, and if it's unencrypted, one could take a look at what's happening there, right? Speaking of digital, they also promise that the devices, the protocol is fully digital, meaning that, even though you have these crappy wires, it just runs, it just works. And I thought that's fun, because analog is also fun, but digital is a bit more fun, a bit more challenging. And they also promise encryption. They say, information will be encrypted, at least the audio and video information on the bus will be encrypted. So that also sounds fun. And then the wires are non-polarized. Now, 2 wires without polarization. I was really, really stuck about what that means. So yeah, we'll see how that went. So, and one more interesting thing is the system is user swappable. So here's a video of someone from Fairmont, Australia. Imagine that's the sales department. So what they have on the table currently, what they're removing is the old home unit. So that's the phone that you have, right? And their goal is to attach a new one that has a screen on it as well. So, upgrade. What you see on the table as well, on the right, that's the device that is downstairs. That is it's called an amplifier, basically, the central part of the system. And on top you see the power supply. It just supplies filtered voltage, and that's it. So nothing magical. Now what happens here is they finished upgrade from audio to video. So a user at home has just swapped their terminal. That is what has happened here. And now look at how it gets onboarded into the system, right? You just power it up. And what you need then is you need to enter the address of the device. And the address of the device is simply 00 and then 4 digits for the apartment number. That's the address of the device. That's how it swaps. And then you can test it from downstairs. You can dial the apartment number, and it connects. So that didn't make too much sense to me. And I've been doing engineering and reverse engineering for a while. So I thought there are a couple things that may have happened there. Either all devices in the world come with the same key, which is somewhere inside the firmware, and it just magically works. Or second option is that at the moment when the device is connected, the amplifier sends the cryptographic material to the device. So those were the only 2 options that came to my mind. So I thought, OK, that's fun. Let's take a look, right? The prompt is encrypted. It seems easy enough. Let's hack it. So that's how my reverse engineering journey started. So these are the steps I took. And through the slides, you will see I'm standing in front of it, but some of you will see on the bottom right corner, there will be different devices popping up, different tools that I used to get this far. Now, for now, we just have one icon there, and that is the terminal itself, right? It's just the phone terminal itself, right? So the first step, of course, is opening it up. You expect you're going to open it up. They come with instructions on how to close it, so you reverse instructions, you can open it up easily. It took a while. This was one of the longest parts of the reverse engineering process. The reality wasn't that good. I kind of pulled it out of the wall. So then I had this huge hole in the wall there. But I did get to it. I looked at the terminals. These are terminals. So you have there's the A and T is for amplifier and for the bell button if you want to connect it. And the bus itself, DUOX PLUS bus, is marked B. Non-polarization is emphasized by both of them being marked the same. So B and B, right? And what we see here is basically installer used the Cat5 cable to connect connect both wires of the bus, right? Just to limit the voltage drop. I think that's the reason why there are so many wires into each of them. Then, since the opening didn't go that well, I made sure to never have to open it again. Just added some wires that way, so I can access it at any time. And I also fixed one of the holes there. Now, the next step, of course, is to measure voltage. Now, you would need a voltmeter for that. And for now, we have the device, the screwdriver, and some wires. Now, measuring between B and B, I got about 24 volts DC, which very acceptable. It says fully digital, 2 non-polarized wires. Ooh. So I was stuck for almost a month thinking about what non-polarized means. That's where I was. I measured 24 volts, and I thought, if it's DC, how is there no plus, no minus, right? And I was just looking at and hypnotizing it and thinking, and then a month later I decided to solve the probes and measure it the other way around. And obviously it's minus 24 volts DC. Like, what was I thinking? I have a master's degree in physics, so how did I get stuck there? I don't know. Obviously unpolarized was a lie, right? There is polarization. One of them is positive, one is negative. What they mean is you can connect them either way, and the board will take care of it. Right. Then the next step would, of course, be to measure voltage during incoming call. Anyone here old enough to remember the telephone system? Okay, 1/3 of you. Anyone played around with it? Yeah, okay. So what happens during the call, right? During a call, where I come from at least, you get a lot of voltage when call is coming in. In Eastern Europe, Latvia, 12 volts DC was the idle voltage for it's just to support everything. But when the call was actively coming in, you had 110 volts AC, which is because the bell was connected directly to the same 2 wires, and there was a solenoid, and you need to move it, and it takes a lot of voltage to make the sound. Just for the bell, it hit like a bell. So here I did the same thing. I measured during a call, didn't see anything terrible. So still about 24, 25 volts DC maximum. So I've got this thing. I think these days you can get one of these like for €5 on somewhere, wherever people buy stuff these days. It's a clone. It can kind of tolerate 5 volts, according to my own experience and anecdotal reports on the internet. Officially, it's I think 3.3 volts, and it's 24 megasamples per second, which is amazing. We'll get back to that later. So, but the signal is 24 volts, which is way above 5 volts. So what you do is, of course, you need to understand if it's gonna, how it's gonna work. Now, the tolerance on Salaya is it registers low when the voltage is under 0.8 volts, and it registers high when the voltage is 1.2 volts or higher. Well, I found some capacitors at home. Specifically, back when I was a kid, I was about like 7 years old, 10 years old. Soviet Union had just collapsed, and all the families in Soviet Union had this understanding that you have to save stuff. You can't just throw stuff away. So what I was doing, I was dismantling old TVs and pulling caps and other electronics from them. So I just found one of these last year at home, and I thought, that might work. So luckily, I do have a detector that tests different electronic components. I plugged it in, and it still worked. 35 nanofarads. It was relatively stable. Then interface had to be designed. So here we connect to the B bus. Just take one of them as the ground and the other as a signal, and we can then receive at the end of the cap there. If you want to transmit, we can use the transistor over there, but we can receive at the end of the cap. So very simple, basically. It's just the cap coming in through there. Right, and then I remembered I have an oscilloscope. Well, it's a joke oscilloscope. It's not a real one. You can get this. I don't know how much I paid for it. Probably a bit more than €5. But still, it didn't even have like the sampling rate or the maximum bandwidth anywhere. You had to like look deep in the spec or the source code. I don't recall. So what you can see is on the bottom right, I actually used a marker to mark it when I bought it, so I know that it's only 200 kilohertz, right? So I connected it this way through the cap. So we limit the signal, right? It's not 24 volts anymore. We remove the DC base that way. And we have a signal, right? We have digital signal coming up and down. You can kind of imagine that you can see, you can decide what the bit width, what the symbol width is, and you can kind of see them going up and down. So that's cool. That should work. So back to Salaya, which then can be used to dump the digital data, right? It can't see the level, but it does have these thresholds 0.8 and 1.2. And here we can see that exactly crosses over that level, which is really nice. So we start dumping with it. Anyone of you have worked with Salaya? Yeah, half, more than the pods. OK, so what happens with Salaya is, of course, if you try to capture 24 megasamples per second, nothing happens. It just doesn't work. You get 0 symbols coming in. So you can try to downgrade it. Capturing at 12 megasamples per second works a bit, right? You can capture for, depending on your luck or other physics, you can capture for maybe 100 milliseconds, maybe 500 milliseconds if you're lucky, and then it just crashes. So as everyone that has worked with Salaya knows, of course, the standard bandwidth that uses 8 megasamples per second. That is the stable one, the one that actually gives you the data. Speaking of which, here's the data, and you can see like looks like there are some frames there on the top right. You can see it really looks like a burst of frames. And if you zoom them in, that's on the bottom. Each frame has a structure, right? You can kind of see that some data is coming in there. So I thought, oh wow, that's great. So now the question is, what data are we looking for? We should try to decode the symbols. There might be some checksums. There might be some encoding to it, right? It's very likely 0 is 0, 1 is 1, but maybe not. So we need to understand some data that we should expect there. Well, from the video before, we saw that the apartment number was programmed, and it was 6 digits. And I found a documentation that gives you a breakdown. So you have the block number, which is 00 to 09, which is most likely for installation that I had either 00 or 01, so just the first block. And then the apartment number, right? So 4 digits. Let's say your apartment is number 12, so it's 0012. So I would be looking for a bunch of zeros and then 12 in the end. So you try to look at that and you try to understand what's going on there. Unfortunately, in the tens of dumps that I did, I couldn't find that data specifically and reliably. And so then I thought, OK, let's look at some other data. Let's do a fast Fourier transform because the information encoded in the audio uses FSK, frequency shift keying. So you should be able to see the frequencies on the graphs. There you go. That's what we have here. A waterfall graphs. We do see some frequencies, and we do see them moving up and down, right? So then I spent some days looking at the graphs, and I was trying to find it. So I was looking and seeing, is it there? Well, still couldn't find it. Wasn't there. So I went to look at the patents that this nice company has published, and they are quite specific. Any one of you who have worked with patents, or most likely reading them rather than writing them, know that they are intentionally written so that it's a bit hard to understand what they say. So, and here is the same. So they don't give you any specific numbers, but at least it gives you technologies, right, which is good. So what we can see here is multiplexed over time. That means it's TDM, time division multiplexing, right? It uses binary narrow frequency shift keying, so FSK, just very small, very narrow frequency bands. And it can also use pulse position modulation if you're transmitting video, which the device in question that I reverse engineered doesn't have support for, so it's just FSK, which makes it much, much simpler. Actually, before doing this project, I've never seen PPM. I've seen pulse width modulation, but pulse position modulation is something even crazier. So it basically allows for infinite data density depending on the quality of your medium. Quite a cool idea, because the position can be an irrational number technically. So then I thought I need some more data, and an interesting concept that I learned, even though I've been running my own company for many years, I never had any training regarding managing people or running a business, so I didn't know that. But apparently, there are tenders. Government wants to buy some stuff from the private sector. In modern world, they can't just go to some guy's brother and say, hey, let's buy your stuff. They have to make a public tender. So what I didn't know is that companies actually can publish like a semi-secret thing on their web page where there are tender specifications. So let's say a government agency would like to buy this stuff. They go to the website, they click on tender specs, and they have like a copy-pastable Word document. You know, if you want to buy our stuff, ask the market, the free market, to have these features in there, right? So that's quite interesting. In any case, for research purposes, this is one of the documents. It basically says that we have 480p at 25 frames per second for video. It's compressed with H.264. And the audio is G726 and Opus. And bitrate is at least 40 kilobits per second, right? So 40 kilobits per second seems a good bitrate for what we're trying to do, for the technology that I have, right? And interestingly enough, the wires should be able to be as long as 500 meters, which I think is crazy, right? They promise these, that any wires basically will work, and you know, it just, this length, just half a kilometer, wow. And it's not optics, right? So from the documentation, we can conclude we have time division multiplexing, we have narrowband frequency shift keying, or PPM in some case. We have encoding, which is in my case G726 at 40 kilobits per second, low enough bitrate. We know nothing about encryption, so we don't have any encryption technologies. Nothing has been mentioned more than, you know, the data is encrypted, at least the audio and video data. So. At this point, I'm thinking, can I really do it without ordering any test devices, right? Because it's kind of hard to work with a device attached to the wall. And I realized that, yeah, I can. I think I have enough hardware that I can deal with it. Even though still, in the end, I find a really good deal and I order another one, you know, just to take a look at it a bit better. Right, and also, by the way, there are cheat codes for this thing. So this thing exists. It's called the DUOX PLUS programmer. So basically, it can display the data on the bus. It just connects to the bus, and it gives you, you know, these commands have been sent. You can connect it to a computer, and you can actually dump it, like kind in not Wireshark, but kind of like in Wireshark, right? And it was on sale as well. So this analyzer here, you can see its user manual here. So basically, it just says, yep, these are the commands being sent, right? Very nice. So, I mean, it seems like relatively straightforward. So we have the device. It can decode everything except the audio and video. Audio and video is encrypted. We don't know how, so we're done here, right? We can't really do anything about it. Well, so that's when I finally decided that I should take a look at it a bit more properly. So there are multiple ways that we can actually move forward from here. We can either reverse engineer firmware, or we can do differential signal analysis, looking at the live data on the wire, or we can also do live probing. You know, have the system running and just probe around the test points on the board and see what kind of data we have there. We can combine those as well, of course. So I managed to talk to some nice people, some hackers who have been solely focusing on signal processing, and I showed them my research at that point. And the thing one of them said is, here's a quote, your data quality is likely insufficient. So I have a friend with a real oscilloscope. So up until this point, I believe any hacker had these things at home. Now, real oscilloscope, that's probably, you know, signal people have it. Hardcore hardware reverse engineering people have it. The ones that don't just dump the firmware and then, you know, move on. I didn't have it. So but I did have a friend with an oscilloscope. So I invited him to come over, and we connected it to the bus. First order of business is I wanted to see if my Soviet Union capacitor did anything bad with the data. So I connected one of the probe ends to the capacitor, through the capacitor, and the other was connected directly to the bus. So the yellow one is directly to the bus. You can see it's around 24 volts, and the blue one is connected through the cap. And if you take a look at it, at pulse level, it's perfect. It's perfect. Like, the signal is almost exactly the same. It's way over the margin of error. So the cap was okay. It wasn't the problem there. Then we thought we'd dump some of the data using the oscilloscope. So here's a graph that compares the Regal data in red with Celaya in yellow, in gray. And we can see that it kind of matches, right? We see there are these overlaps on the top right where Both of them have a frame there. Well, let's zoom in. If we zoom in, it kind of looks good, but we see that there's this half level in red at the very beginning for the oscilloscope. If you zoom in even more at the symbol level, we see that it isn't that good anymore, right? So we see that Wriggle stops capturing data a bit faster, and then it begins capturing it a bit later. It's not a bug in the oscilloscope, obviously. It basically just means that something is wrong with my setup using capturing using Celaya. And if I try to rescale it so that it matches, then the next frame will be desynchronized again. So that means it's no good. We cannot really do anything much with the data from Celaya. Well, but luckily I have this friend over with an oscilloscope, so we decided to do some dumps. And one of the dumps we do is, just looking at the bus while sending something over the wire. Over the microphone. I hope you can kind of see that. So I'm looking at this signal and I'm thinking that's interesting. And then I remember this thing, ECB Penguin, right? That's an example is about 15 years old. Basically, it shows you how if you use block encryption without combining the blocks, without interchaining them, then it's all bad because the same color, the same color sequence and sequential pixels result in the same encrypted blocks, and you can still see the content. Now, and looking at the picture that I got from the oscilloscope, it kind of seems that there's something there. Something isn't really clear there. So what we did is we actually send 440 megahertz, 50% duty cycle over the microphone while we were recording this. And you can kind of see when there's the 1 second when we're sending the audio, it really raises the signal level there, right? So it kind of indicates to me that if the encryption is there, then it's terrible encryption because, this is a very simple signal, but you can still visually see the signal on, off, on, off, on, off here in the Fourier transform. Now, looking at the time frames a bit closer, we can see time division multiplexing is really there. So I marked them with blue, with cyan and purple. So there are 4 slots. And by the voltage, you can see that the first slot is downward facing, so to the phone. Second slot is upward facing. Why? Because the voltage is higher, and I'm capturing at the phone end, which means that's where the stuff is coming from. That's my assumption here. And then we have 2 empty slots in purple because the system does support 2 simultaneous conversations according to the specs, meaning that 4 people can talk, right? If you have enough devices on the bus. And also according to the spec, apparently you can call a different apartment. I don't have any buttons for that on my physical device, but according to the spec, you can call apartment to apartment, which also seems like kind of a fun thing to do. Right. So, BNFSK, right? That's what it does. Basically, use a pair of frequencies to represent each one of the 2 values, ones and zeros. And the third frequency is used for frame start alert. This is from the patent. And here we go. If we take a look at the data from the oscilloscope and we do a Fourier transform, we actually can see right here the beginning of the frame, third frequency, and then we have kind of can see 2 frequencies going there, jumping up and down for the rest of the data, right? If we zoom in, there we go, quite nice. So that's the start, and these are the 2 frequencies that we have in there, right? So problem solved, right? So I did manage to conclude that the frequency for zeros is 2.3, frequency for ones is 2.5, and the start frequency is 2.6 megahertz for this protocol. Now, then me and my friends did some magic to process it, basically applying these nice magical signal processing stuff to it, Butterworth filter, Hilbert transform, and then instantaneous power, and this is what we got. So these are 3 different bursts. So at the very beginning, I believe it sends multiple one frame multiple times because it doesn't receive the acknowledgement that the frame has been received. So it's the same data. And you can kind of see that, this is probability plotted on the vertical axis. You can kind of see that synchronization signal 2.6 megahertz is at the beginning. And then we clearly see zeros and ones, right? So it's very stable. Basically, it's a good match right here. Well, which then means that we can convert it to symbols and bits, right? So here we go. Sync 0, 1. Data. OK, so then I felt we need some more data, and we should go the reverse engineering the circuit board kind of way, right? And anyway, if there are hard-coded keys indeed, then we need this anyway. We need to dump it so we can see what the keys are. So there are some limitations when doing reverse engineering. For example, here we can see this is the board. I zoomed it in, and we can see multiple things here. One thing is that 3 traces are just going under a bigger device, bigger component, and we cannot really trace them visually. Another thing is some of them are going through the board to the other side, which is manageable. So regarding the first problem, either you can have an X-ray. Anyone has an X-ray for this purpose? No one? Yes. I was just. I came directly from Recon, which ended 3 days ago in Canada, in Montreal, and different crowd. Recon is a reverse engineering conference. They're like every second guy has an X-ray. So yeah, I don't, obviously. The other thing you can do is you can use a heat plate to desolder the element, right? But then you need 2 devices because you might want to put it back. You may be able to do that, maybe not able to do that, right? So that's a limitation. Another option you can do is you can do continuity probing. So you can just use probing to connect the pins on the chip to the test points on the board, or different traces on the board. You can clear a trace up and take a look at that. So that's another thing you can do. So that's the board. There are different hardware versions of the board. This is just one of them. And it's quite populated, has a lot of stuff on it. So let's go through it, right? The next step is you kind of try to understand what's there and see what components are which. So the first one is the inputs and power circuit. As you imagine, this DUOX PLUS bus, these are only 2 wires coming in. I didn't mention specifically, explicitly, but it's 24 volts to feed the device, and it also modulates data over there, right? So that's what this stuff is doing. Okay, what else have we got here? We've got the hook for the handset, where you put the handset on. We also got the connector for the handset. And we have some buttons, right? We have the volume switch here. We have the door release button in the middle, and we have the programming button here on the, well, relatively bottom, but in this case, you're right. Then what else do we have? We do have an oscillator, so 8 megahertz oscillating crystal here. So that's our clock, which means that whatever we're doing there, the max frequency that we might be dealing with is 8 megahertz, right? So that's way different compared to 40 kilohertz that we were potentially looking at earlier. And it's just at the border of the 8 megasamples per second that SLI can capture. And you cannot really use 8 megasample capture for 8 megahertz signal because you're just gonna, you don't have enough data points, and you may arbitrarily end at different phases of the signal. That way you don't have any good data, which is the reason why SLI didn't work. Now, then we have these nice, 3 nice packages, right? 8 legs, 4x2. And when you see those, the first thing you think, wow, let's dump some EEPROM. Well, looking at them, none of them starts with 24 or 25. All of them are actually op-amps, so amplifiers. Very, very disappointing, which means that our code that we're looking for is in the microcontroller, which is ARM Cortex-M, Cortex-M4, in this case done by Nuvoton. Oh, and finally, there's another thing that attracted my attention. On the very left, there is a connector. It's serial wire debug. And one important thing about it is you can see that someone had soldered there before. So that means at the factory, as part of testing or programming every single device, they are actually soldering a connector on there. Which means there is a slight chance that it's still electrically connected, and maybe maybe the microcontroller isn't locked. So we can try to use that. And there are a bunch of test points on the other side. So that's the MCU that we have, ARM-based microcontroller. In our case, it's this one here. So it does have CAN bus and USB, which, while doing my research, it kind of turns out that it's not being used. So I'm imagining maybe it's a sourcing issue why they're using this one, because I couldn't see anything of these functions used at all. Right, and SRAM is 32 kilobytes, and flash here that we have is 128 kilobytes, right? So this one right here. And here are our pins. This is our SVD. Nuvoton calls it ICE for some reason, integrated chip something something, but it's still serial wire debug, so SVD. So a quick solder job later, that's what we got. I soldered the pins. I connected it to an ST-Link, and we dumped it. And then we can finally go on to reverse engineering the actual firmware. Oh, and before this is kind of the last big chapter. Before I started, I would remind you that this is aimed not only at seasoned reverse engineers, but also at people who would like to start there. So don't be afraid to ask questions if you're one of them. At the end, we're going to have a couple minutes for questions. Just you can ask any basic questions as well as hard ones. All right. So I dumped the file. It's 128 kilobytes. And it's no surprise ARM Cortex-M firmware. Well, I was surprised that it dumped successfully, but here we are. It has all the vectors at the beginning, so it seems very nice. Then the next step you do, obviously, is you do bin walk. Oh, nice, yellow works in there, and you take a look at what's in there. Now you can see that firmware ends at about 90 kilobytes there, and 0.8 entropy. It's random, a measure of randomness, basically. 80% entropy usually indicates machine code for ARM, right? So we have a bunch of code at the beginning and a bit near the ends there. Then at 0.6 entropy, we have strings. This is usually English text, and we have two places, just before the last spike and just after the last spike. That's where we have text, and it's quite a lot of text. It's usually in a firmware like that, you wouldn't expect that, because this device that I'm reverse engineering, it has no screen. So there's nothing to display the text to. So it shouldn't have a lot of text, but it does have quite a lot of text. And then finally at 0.5 there, we have some tables that have to do with audio processing and digital signal processing. So some constant tables there. And inside, we really do have a lot of strings. So in this relatively small or large, depending on how you look at it, about one string per kilobyte of firmware, right? Which isn't that bad at all. There are also two unique paths in there. We have the fast Fourier transform library by KISS. It's open source. And we have also another open source component, randomization function that randomizes stuff. By the way, randomization is used in protocols like that for two things. Well, if it were used for cryptography, that would suck, because this is not a cryptographically secure randomization. And the other thing that it can be used for is anti-collision. So basically, it's a bus system. There are many devices. If all of them were going to communicate after the preset amount of time, we would have collisions all the time, which means that they tend to randomize the delay before they send some data on the wire. That's where the randomization function is usually used. And well, looking at the firmware, I did discover some interesting stuff. So far we've had the discovery of the data being weakly encrypted, that you can actually see it on the wire. And you can also, I don't like how my dumps are looking here on this projector. I'll try to read the most relevant part to you when it's needed. So here in this case, line 52 on the top, it basically says it's a switch, and it says case 33. And then we have line 73 on the bottom, which says if command 2 equals 0xAA. This basically checks if the 2 bits of the command coming in are 33AA and enables programming mode. Basically sets programming mode to on. There's another place in the firmware where the other command is 0088, does the same thing. So basically, looking at the firmware, the reverse engineering of the firmware, what we can see is that anyone on the bus sending in any of these 2 commands immediately can put any device that this is addressed to into programming mode without any authorization or anything. And then you can start reconfiguring it. Well, to be fair, there isn't much you can do. You can do a couple of things. You can change the melody of someone else's call. You can remove it from the network, or rather change its address. You can, of course, also change your own address. And finally, you can enable something called Doormatic, which is formatting. It's a port menu of door and automatic. As far as I can understand from the firmware, it basically means that if someone calls your apartment, the device will immediately, well, automatically open the door after a preset delay, right? So apparently there are these installations where you're calling just the correct apartment will automatically open the door without human pressing a button, which is also quite fun. Right, and the frames in DUOX Plus use checksums, very, very simple checksums. Usually there is some magic constant involved, not here. Basically, there are 2 checksums. There's a XOR of all the words, so basically 4 bytes that XOR everything and they are added together. And then there is 1 byte, which is in sum of all the bytes, modulus 256, of course. So finally, the last thing that remains unanswered for me is the encryption. How does it work, right? And that's the main reason why I dumped the firmware. So I decided I should kind of draw the path from the microphone on the phone up to the wire. So how does the data get captured on the microphone and how it ends up on the wire, all right? Because encryption has to be in between there. Because microphone is analog, that's just you speaking, and bus, then that's encrypted already. So that's what I'm looking at now. Let's take a look at it. Okay. Let me, interesting, why is it black? I see it here. Let me try one thing real quick, sorry about that. I know of one LibreOffice bug that can do that. No, that didn't help. It's probably something with that stuff over there. OK, right. So what we're supposed to have on the slide here is a dump of a function that controls the audio codec, and specifically gain volume control function. So since it is gain volume control function, wow, that's unreadable. Since it's a gain volume control function, it basically means that it works with raw audio, because you cannot do gain control. You cannot adjust the volume on a system that's encrypted, right? It has to be unencrypted. So that's what we have there. That's the first function. Ah, there we go. At least this slide works. Interesting. So what we see here then is a different function. This function calls the previous function. It calls the codecs gain control select. It does so on line 61. You can see it. You can almost see it right there. So it calls codecs gain control select. And this function is called codec prepare TX frame. And what's interesting is that on line 61, it calls this function that works with analog audio. And on line 71, it sets a flag called DUOX TX ready, which basically informs the protocol code base that the voice packet is ready to be sent, right? So it just copies it on the stack, and the analog data is copied on the stack and says, hey, OK, we are ready to continue processing of it. So basically, the function we just saw calls the first function and then sets the DUOX TX ready to 1. And this is the main loop. That's how it all comes together. So basically, there are interrupts, of course, as with any hardware. But this processing is done, outgoing processing is done through the main loop. We have 500 nanoseconds delay, so half a millisecond. And then 2 functions are called. main tick process DUOX link. Of course, it's my name. I don't know how they call it. And then there's a custom function that usually processes audio, and that can be set to something. This is classical way to do it in real-time systems. So basically, we have some limited amount of time where we can run some code, and so each time we need to run something else, we just change the pointer and call a different function. So that's how it's all set up, right? So we have the main function on the very top here, and on your left there's the custom call that called the audio and set the DUOX ready to 1. And on the right, then that's the other function that we just saw, the main tick process DUOX link. That's called there, right? So let's take a look at it. This is the function. This is main tick process DUOX link, and it forms data packet when time division slot is available. So on line 36, you can see that it calls DUOX send function. And so basically, that's what it does. Depending on the loop operation. So we have the case 0, case 6, and so on. So it's similar to the custom exec address. Here the technology is different, but it's the same thing. Like every loop you run it can change the operation depending on a variable, right? The second one uses a pointer. The first one uses memory address to decide what is going to be done. So this is then the main ticks process DUOX link, which, as I mentioned, launches on the bottom you can't really see it, but it launches the DUOX send command. So that's how it looks. It checks if the loop operation is 0D, and if DUOX ready is not 0, which is set by the left branch, and then it launches DUOX send. Looking at DUOX send, it basically copies the data in the right space in memory depending on the channel, right? There are these 4 channels, well, 2 channels for outgoing that you can use. So that's what it does. And on the bottom, line 24, it says DUOX ready hardware 2 equals 1. Right, so that's like the next step of processing. So this function, all it does from the beginning to the end, just copies the data. No processing, doesn't change the data at all, right? Right, so at the bottom there, you can see that it copies it a specific memory address, and it sets hardware 2 equals to 1. And then in different loop operation number 0x10, it checks if hardware 2 is not 0, and then calls function pvm-tx hardware 2, which is fully on the script on the screen here, right? So on line 12 we have a mem copy. It basically copies the data prepared by the previous functions to pvm output buffer, which is a hardware register, and then on the bottom 27, line 27, it basically sets the PVM output buffer and asks the MCU to actually send it. So this is where it's being sent on the wire, right? So this here, which is barely visible, basically indicates that I couldn't find the encryption. From the microphone to the wire, everything is processed. We do some codec, playing around with codecs like gain control, but there is no encryption there. So that's where we are basically with the research. So encryption wasn't there, which is very, very disappointing. It would be fun to do some injections, obviously, take over some phone devices of other people, but that would be illegal in this setup. I would need to build my own test rig with many of them. Right. So that's where we're at. And yeah, let me know if you have any questions. I also want to do a shout out to a bunch of people that helped with small things here and there, that lended their expertise for me to understand signal processing a bit better. And once again, Kurils.org is where all the slides are, and you can follow me at chaos.social on Mastodon as well. Thank you so much.
All right, are there any questions? Do you see any hands, any questions? Maybe I start with one. In the beginning, when you explained how the wiring works, I wondered if this is one bus going through the whole apartment, isn't this not totally error prone. If somebody, and if it's even user switchable, then some user fucks it up and connects the wires, and then the whole apartment goes down, like from the intercom wise.
Yeah, exactly that. You're exactly correct. According to installation documentation, if you have more than, I don't remember the number, I think more than 40 or 50 apartments, you're supposed to use like signal separators in between for some reason. But yes, in an installation with less apartments than that, it's just one bus going everywhere, and yeah, if you short it at one end, then you're done. I think you might even be able to burn out the power supply that way. I haven't tried it, of course.
Not even
It's fun, yeah.
All right, thank you. Any other questions from the room? Oh, there's one.
In episode with PCB reverse engineering, you said that you would need an X-ray device or at least a heat plate to see the routers under the chip, and so. Why they using chip heat gun to remove ICs and then put them back is not an option?
Thank you. So the question is, why would I need X-ray or heat plate if I can just use a heat gun? Well, I'm just not good enough with a heat gun.
So it's easy to use. You just need a half an hour to train.
Thanks. I'll try that.
All right. Another question there.
Looking at the whole design, it looks exceedingly primitive and not only unsecure, but unreliable. How could this be a near world market leader in this field?
Can you elaborate on the unreliable part?
Unreliable, you say any wiring can be used, so for the bus. Knowing building installations, it's exceedingly likely that somebody puts a voltage onto it whilst fiddling with the installation and blowing the whole thing up.
Well, it's yeah. In a way, you have a point, right? It is supposed to be installed by professionals. The initial stuff. Any wiring part is meant for to capture the market of all the buildings. Not relatively many buildings have been built, and not that many buildings are being built at the moment. Like if you compare those two groups. So what they're trying to do is they want to kind of say, if you have this very old intercom, like a primitive intercom system that would be an analog system, just two wires, just sending audio signal, right? And they are saying you can just use the same wire, you don't have to rewire your whole building, right? And usually these wires are not something you fiddle with, right? Because either they're hidden in the walls in an apartment building, or people just don't generally go through the stairwell and cut wires and poke at them, right? So the only place of risk is the sticker on the device saying in your apartment, hey, you can replace it. I don't think that an average person would replace it themselves. I think seeing the sticker, an average person would call someone to come and do that, someone who knows how to do electrical stuff. And even though this is not high voltage, it's only 24 volts, it's similar to how you do high voltage. Well, is it high voltage? Anyway, how you do household installations, 240 volts. You would usually call someone else to do that, because you can do the same with your lighting, right? In your home, just connect the wires, and it's not going to work. But it is true that, of course, here you don't have breakers for your apartment, so you would remove the whole ability of the whole system to operate.
I came to this question because I've done many repair on Spanish installations in buildings, signal installations built from the 60s to the 80s. And what you find there sometimes is interesting from the safety point of view.
Yes, I can imagine, yeah. And at least in Latvia, the same also applies to 240 volt installations. There are many house fires that happen because of different ideas of how installation should be done. Absolutely, yeah.
All right, maybe one more question. Okay.
First of all, many thanks for the talk. Very interesting and very nice to stick along on your journey, let's say. My question would come to what you've mentioned at the very end, let's say, so the encryption and specifically the missing part. So I'm no expert on this, but maybe you have further insight. Could it be that it's not done in software, but rather maybe done in hardware, and that the software passes on, and even before it's transmitted on the wire, actually, it's still manipulated?
Okay, that's an interesting idea. So, the reason why I went in the software up until MCU actually sends modulates the signal is, to make sure that it's not done on the MCU. So, it is. We verified that it's not done in firmware, and we verified that it goes out of not these pins, but it goes out of the relevant pins out of the MCU, right? So that's the data that comes out. So then your question basically becomes: is it possible that somewhere here there is a component that does encryption on the signal? Well, I don't see any, because the 3 4x2s are op-amps, and then all the other components on the board are 3 pins maximum. Well, we have some filters there as well. So there just aren't any components on the board that can do that. And do recall that I did the dump of the signal, and you can visually see the audio being sent.
Thanks.
All right, and I think if any of you have any more questions, then just feel free to approach the speaker after the talk. Let's give another round of applause.
Thank you very much. I'll be around until tomorrow's evening. So yeah, I'm happy to chat with any of you. Thank you.